Welcome everyone. I am absolutely thrilled to be your guide today for this explainer. We're going to be visualizing the phenomenal biological machinery that takes a tiny, totally invisible electrical impulse and turns it into real, earth-moving physical force. Let's map out exactly how our bodies are actually working down at the microscopic level.
So, let's kick things off with a massive question. How exactly does a mere intention in your brain translate into the sheer mechanical power you need to lift a car? I mean, it sounds kind of like magic, right? But as we'll see, it's actually a highly engineered, step-by-step biological process.
To answer that, we're going on a chronological journey. We'll be looking at the body's electrical battery, firing the action potential, crossing the synaptic gap, mechanics of muscle contraction, tuning muscle force, and lastly, when excitable tissues fail.
Section 1. The body's electrical battery. Let's start right at the baseline state of our cells. We really need to separate two foundational concepts here. You can think of a cell's excitability as essentially its flinch reflex, its ability to simply react to a stimulus and change its membrane state. But completely separate from that is conductivity. That's the cell's ability to actually take that reaction and send it down the line as a moving spatial electrical wave.
Now, to prepare for that moving signal, our cells actually have to build up a charge. Picture a sort of cellular water wheel sitting right on the membrane called the ATPase pump. It is constantly throwing 3 sodium ions out of the cell while only pulling 2 potassium ions back in. And because it's pushing more positive charge out than it's bringing in, the resting baseline sits steadily at negative 70 millivolts. Boom, your biological battery is officially charged.
Section 2. Firing the action potential.
Okay, so the battery is ready to go, but how do we trigger the spark? Well, it requires an action potential, which is this massive all-or-nothing electrical surge. First, a stimulus hits a threshold of negative 55 millivolts, and suddenly it's like cellular dams just burst open. Sodium rushes in, causing the internal charge to flip and spike all the way up to positive 35. Then, in step 2, those sodium gates slam shut and potassium rushes out to restore the negative charge. But because those potassium channels are kind of slow to close in step 3, the voltage actually overshoots. It dips all the way down to negative 94, before finally fully resetting.
Now, as this newly generated spark travels down a nerve fiber, we see 2 entirely different speeds depending on how the nerve is built. An uninsulated wire, an unmyelinated axon, uses continuous conduction. This is a very slow step-by-step process, but if you wrap that axon in a myelin sheath, the electrical signal literally leaps from gap to gap, these are called the nodes of Ranvier, at absolutely blistering speeds, which also saves a vast amount of cellular energy.
The physical structure of the fiber directly dictates the speed of the message. If you look at heavily myelinated type A alpha motor fibers, they are firing at an incredible 70 to 100 meters per second. That's the lightning-fast reflex that moves your arm away from a hot stove. Meanwhile, unmyelinated type C fibers carry that chronic, dull, throbbing ache you feel long after an injury, and they do it at a sluggish 0.5 meter to 2 meters per second.
Section 3. Crossing the synaptic gap.
As this high-speed electrical spark reaches the end of the nerve, we arrive at the neuromuscular junction. This is where electricity has to translate into chemistry. The arriving electrical signal triggers a sudden influx of calcium. This acts as the ultimate trigger, causing the cell to dump chemical messengers, specifically acetylcholine, across a microscopic 15 to 20 nanometer gap called the synaptic cleft, where it locks right into receptors on the muscle side.
Section 4. Mechanics of muscle contraction.
And that chemical handshake across the void brings us to the actual mechanical generation of force. When the chemical signal hits the muscle, it dives deep down into the T-tubules, releasing even more internal calcium. This surge unlocks these tiny, highly organized functional units called sarcomers. Visually, you can think of these like microscopic overlapping gears, made up of thick myosin filaments and thin actin filaments.
This sliding filament mechanism is the exact precise moment thought becomes movement. Fueled by cellular ATP energy, these tiny myosin heads start out in a cocked state. Once calcium exposes the binding sites on the actin, the myosin grabs on. Then comes the power stroke. The myosin neck physically snaps inward, pulling the actin filament roughly 10 nanometers towards the center. Finally, a new ATP molecule binds, releasing the head to start the entire incredible microscopic cycle all over again. It is literally pulling your muscle fibers shorter.
Section 5. Tuning muscle force.
But you know, lifting a delicate feather requires a very different level of force than lifting a car. To manage these different tasks, your body essentially recruits different engines. Type 1 fibers are your slow twitch muscles, relying on oxidative energy. These guys are your endurance marathoners. They keep you standing all day long without fatiguing. On the completely opposite end, type 2X fibers use fast-burning anaerobic glycolysis. They are your explosive sprinters that tire out in seconds but deliver absolutely massive rapid power.
Your central nervous system acts as a masterful conductor for these different engines, organizing them into motor units, which is basically a single nerve and the exact muscle fibers it controls. For delicate precision, like eye movement, one nerve might control just 5 muscle fibers. But for massive power in your quadriceps, one nerve might control 2,000 fibers. And the whole system strictly follows the Henneman's size principle. The delicate, fatigue-resistant units are always recruited first, and then it smoothly calls upon the massive power units only as force demands actually increase.
Section 6. When excitable tissues fail.
Unfortunately, this highly sequential pathway is incredibly vulnerable. Whether it's autoantibodies from your own immune system or external toxins, a disruption to our cellular battery, the high-speed electrical propagation, which is what we see in things like multiple sclerosis, or even just that chemical handshake, can bring this entire powerful system to a grinding halt.
Diagnosing these breakdowns requires incredible visual and clinical precision. Take myasthenia gravis, for example. It's an autoimmune condition that destroys the acetylcholine receivers on the muscle side, meaning weakness worsens drastically the more you try to move. Conversely, Lambert-Eaton syndrome blocks the calcium channels on the nerve side. In that totally unique case, repetitive use actually helps build up enough calcium to temporarily force an improvement in strength. So you have the exact same overarching symptom of weakness, but stemming from 2 completely different microscopic breakdowns.
Which leaves us with a truly astonishing thought to end our explainer on today. We know that a tiny drop of tetrodotoxin from a pufferfish can irreversibly jam our cellular voltage gates and halt this entire electrical system in seconds. But looking at the exact biological mechanics we visually mapped out today, what are the ultimate limits of human strength and endurance if we learn to fully master and perhaps safely upgrade this excitable machinery? Thank you so much for joining me on this journey from spark to movement. Keep questioning and keep learning.